Okay, so we'll go ahead and start recording, and I thought it would be fun to do a little application of kind of Markov chain Monte Carlo, because so far all of we've been doing Monte Carlo methods, and we started looking at the Metropolis algorithm, and we've been using it to generate values from random distributions and things like that, and that's fine, but we have a lot of other ways to generate values from random variables. But there are certain applications that can really will really rely on Markov chain Monte Carlo to kind of to solve the problem. And so here's kind of an application of it, and I thought this was kind of a neat one. And so so what we're going to take a look at is we're going to look at kind of figuring out a substitution cipher. Okay. And so, I don't know if you ever did this when you were a kid, and you tried to pass messages to a friend, or oftentimes maybe like on the back of a cereal box, they would have these little puzzles and you'd have to figure it out or something. And basically a substitution cipher is all of the letters in the alphabet get mapped to different letters in the alphabet. Okay, so for example, this could be one possible letter mapping, and if this was the cipher key, okay, then the message hello friend would get ciphered into H would get ciphered into a B, and then E becomes a U, and L becomes M, and then we get the text BUMMI JKFUNO. Okay, and so this is the ciphered message, and you could use this to like try to pass messages to a friend in school or something, so that if the teacher intercepted your message, they wouldn't be able to read it or something like that. Okay, and this was actually what was happening in a prison was that the prisoners were passing messages to each other, but they were using a cipher. Okay, they were using some kind of cipher to kind of not really encrypt the message, but cipher the message, so that when the prison guards caught them and found these messages being passed, that the prison guards weren't able to understand what they were saying. And so the question is, if we intercept text that looks like this, BUMMI JKFUNO, can we figure out the original text? That's kind of that's the problem that we want to be able to solve. Okay, we want to be able to figure out what the original message was if we intercept text that looks like this. Okay, so does that kind of make sense? How a substitution cipher works. We're just saying, okay, H becomes B, E becomes U, L becomes M, O becomes an I, and so on and so forth. And then to decipher, you'd look up, kind of the mapping, and then try to translate it. Okay, and so what we need to be able to do is we need to be able to kind of compare potential keys as a way to try to decipher the text. Okay, so I created these potential keys, just kind of arbitrarily shuffling the letters around. And so I have potential key 1 and potential key 2. And what we're going to do is we're going to use these potential keys to decipher the text. And we're going to look at what the how these keys decipher the text. Okay, so if the intercepted message is BUMMI JKFUNO, and I apply potential key 1, okay, this is what the deciphered text would end up becoming. Okay, so the B becomes a G. Okay, because when you're deciphering, you have to look at kind of the mapped letter and go backwards. Okay, the U is in the correct spot. The U becomes a U. Or no, I'm sorry, not U. U is not in the correct spot. Okay, because this says hello friend, right? It's supposed to say hello friend, but you know, in our potential key, U happens to map that to U. Okay, so we get GU. The M is mapped to a V. Okay, so we get GUVVW. The I gets mapped to a W here. Okay, and then JKFUNO. J becomes Y. K becomes Q, and then F becomes a P, and so on and so forth. And so this is, if we apply this this key to our ciphertext, this is what it says is the original message. Okay, and then here's another potential key. All right, and if I apply this one, okay, B goes back to R, the U goes back to an A, and then M goes to L, okay, and then I goes to a P, okay, and then you do the other letters and you get this, okay. So both of these keys are wrong. The original key, the correct key is this, and the original message is hello friend, okay. Now neither of these achieve that, okay. Neither of these translate to hello friend, but we might be able to at least compare these and say, you know, one of these potential keys is better than the other. I think we would agree, right? As far as this, like this one, even though it's wrong, this one looks like it gets us a little bit closer to the original message than the one that produces this, right? Because when we look at this, we go, I've never seen a word with two V's in a row. I've never seen a word that starts with YQP. This feels like it's complete nonsense gibberish still, right? So we know this is nonsense gibberish. This is still nonsense gibberish, okay? This is wrong, but so, you know, the M and the L are correctly aligned here, okay? So, because in the original substitution cipher, the L gets mapped to an M, and here we've actually, you know, just kind of coincidentally found that. And so by doing that, we now get this word RALLP, which is not a real word, but it has, you know, some structure that looks kind of like it could be a word, right? It could be a word. So there's, so it feels like it could be, at least this is working in the correct direction here, okay? Because, you know, we've seen lots of words that start with R. We've seen lots of words that have AL and LL. Those are, those look correct, okay? And then we've also seen lots of words that kind of start with CH, CHO, and stuff like that. This is not, this doesn't seem that far-fetched, okay? We still know that this is not the correct message because this doesn't make sense to us, but just the fact that certain letters appear next to each other make it feel like this, this potential key is better than another potential key, okay? All right, so we're going to kind of take that and we're going to try to formalize this into a little bit, you know, more of a probabilistic statement here, okay? And so, so what we want to do is we want to be able to evaluate, you know, the probability of, you know, some potential mapping, okay, where the mapping is going from 26 letters to a kind of another scrambled set of 26 letters, okay? So we want to figure out the mapping given our data, okay? So what is the probability of our mapping? And our data is basically the text, okay? And the text is going to be kind of the intercepted and the kind of deciphered message. The text will be the kind of intercepted and quote unquote, deciphered message. Okay. Now, I have to say, modern encryption, okay, because modern encryption is the same kind of idea of, when you're logging into your bank, it wants to send the information securely so that if the information gets intercepted, the person won't have your bank credentials, okay? So modern encryption is much, much, much more complicated than a simple substitution cipher, okay? Because, as we'll show you today, a substitution cipher can be easily cracked. Well, actually not today, but on Friday, I'm gonna kind of introduce you to some topics here, and then on Friday we'll kind of apply our techniques to kind of crack the cipher. And so substitution ciphers are easily cracked, and so modern encryption methods are much, much, much more complicated, to the point where they're very, very, very challenging, if not impossible to crack. Okay, so anyway, we want to figure out the what's the probability of a given mapping, okay, or a potential mapping given the data or the text. And using Bayes' rule, this is going to be, well, what is the probability of our text for a particular mapping multiplied by the prior probability of the mapping divided by the probability of the text. Okay, and so our likelihood is going to be the probability of the text given the mapping. So we want to be able to, evaluate what is the probability that, basically that this is the original message. Okay. Here we have the prior. That's the probability of the mapping. Okay. And what we're going to say is we're going to say, prior to looking at the data, we don't really have any reason to believe that one character mapping, one set of letter substitutions is more likely than another. Okay, so we're gonna set the prior to be a constant, and we're gonna say basically all prior to looking at the data, all potential mappings are kind of equally likely. Prior to looking at the message, okay, all potential letter mappings are equally likely. Okay, now how many so we're going to just set that to be a constant. Okay, we're not going to say that we believe, it's more likely that the letter A got mapped to the letter B than the letter Z or something like that. Okay, we're going to just say all kind of, before we look at the intercepted message, we're going to say all potential mappings are equally likely. Okay, and then the marginal probability, that's in the denominator. This is the probability of the text. And we also know that this is a constant with respect to the mapping, okay? And this is going to be the sum of the numerator across all possible mappings. Okay, and so if we think about what are all possible mappings, okay, so kind of our state space would be all possible cipher mappings. And there, and what we have is we've got 26 factorial possible mappings. Because when we create a mapping, okay, the letter A can be mapped to 26 possible letters. Okay, and then once A is mapped, okay, B can be mapped to 25. Then C can be mapped to 24, and so on. To one of the other 24 letters, okay. Etc. Okay, so 26 possible mappings. 26 is around 4.03 times 10 to the 26. Okay, so this is a lot of this is a lot of possible mappings. Okay, and so we can't take just a blind brute force approach and try all 10 to the 26 possible mappings. That's just way too many. Okay, but this is so we'll apply the Metropolis algorithm to help us, but I won't get there just yet. Okay, all right. So is this okay so far? All right, and so what we're saying is that the mapping and the text, those are both constants, and so the posterior can just be kind of evaluated, and we can say the posterior distribution the probability of our mapping given the text is equal to the probability of the text given the mapping times a constant. So the prior probability is a constant. And then we're going to say the marginal probability is also a constant. And so this just becomes proportional to the probability of the text given the mapping. And the question is, how do we evaluate this quantity? What's the probability of the text given the mapping? And this basically is the question, given a potential key, what is the probability that the deciphered message was the original, that the deciphered text was the original message? Okay, so this is Oops. Yeah. Did I mess something up? I don't know what I'm doing here. Okay. So if I look at here, let me just kind of copy this. Okay. So with this potential key, the deciphered text is this, and we want to know what is the probability that this was the original message. Okay, and then versus that. Okay, so what is the probability of that text versus this text? Okay, and our intuition tells us that the text RALLP CHOAMX, is more likely, and it's a little bit strange, but it's more likely this was the original message than the original message than GUVVW. Okay. So our intuition tells us that this is more likely than that this message is more likely than this message, and therefore that means potential key 2 is more likely than potential key 1. Okay. Is more probable. Is that okay? Does that kind of make sense? What we're going for? All right, and so here, let me give you your first quiz answer for today. First quiz answer is the letter C. The letter C as in cat. C as in cat. That is your first quiz answer for today. Okay, so how should we go about evaluating this? And what we want to do is, so the first thing we're going to look at is we're going to look at kind of letter combinations. Letter combinations, okay? So, so one way to evaluate the probability of the text given a mapping is to look at letter combinations in the deciphered text. Okay, so in the English language, does anyone have any idea what the most common letter combination is? I guess, two-letter combination. Two-letter combo. All right, we got some good guesses. The most two-letter combo is TH. TH, because it shows up. So we've got the word the. The is the most common word in the English language. It's about 1 in 20 words is the word the, and so TH shows up very frequently, and there's a lot of words that have TH. Okay, a lot of important words, this and that. Those have TH in them. Things like that. Okay, things and that and them. So TH shows up very frequently. H and E also will show up very frequently because of the word the as well. Okay, whereas other two-letter combinations, you know, like JX, how many words have that combination? Not very many, right? So so what we're going to look at is we're going to create a matrix. A matrix of basically all possible combinations. Okay, so we're going to look at the 26 letters plus space. Okay, for a total of kind of basically 27 characters. We're going to ignore everything else. So ignore symbols and numbers and everything else. Okay. And we will look at all how frequent all 27 by 27 possible combinations are. 27 by 27 combinations. Okay, so we're going to start off, we're going to look at AA, you know, how frequent is AB, how frequent is AC, ... all the way down to AY, AZ, A space. Okay, how many words end with A? And then we will start at B and we'll go BA, BB, BC, ... okay, to BZ, B space, okay, and then CA, ... okay, all the way until we get down to ZX, ZY, ZZ, Z space. Okay, oh, actually, and then we would have space A, space B, all the way down to space X, space Y, space Z. If that kind of makes sense. Okay, so there's going to be kind of 27 by 27, and we're going to kind of try to figure out, you know, basically what is the probability of all of these kind of letter combinations. Okay, and so and we would expect, you know, I guess we would have space, sure, sure, space will be there, but I think God, I don't know. I think in the kind of the text processing, we're going to kind of delete everything that's not a letter or a space. Okay, so we're going to get rid of all numbers and symbols, punctuation, things like that. And probably we would get rid of double spaces. Okay, but all right, so we expect TH to be very high, to have a very high probability. And we expect other combos like, I don't know, QJ or something. I don't know if there's any words. Are there any words that have QJ in them as a letter combo to be very improbable? Okay, so how can we even come up with the probability of each letter combo to begin with? Well, I have some code written here, okay? And what the code will do is it will read through a big chunk of text, and it will look at all kind of 2-letter combos and tally, and every time it encounters one, it's going to kind of tally them up. It's going to keep track. It's going to keep track of all of these combinations and just add a tally for each one. Okay, so number of words in a dictionary with that combo. So if we just look at the number of words in a dictionary, so the dictionary, unfortunately, the dictionary doesn't look like English text, right? Because the word the only has one entry in the dictionary and stuff. But then, but if you look at regular English text, the way we speak it, you know, we use the word the very, very frequently, and the word you very frequently, and things like that. And so what we're going to do is that I have the English translation of War and Peace, okay, which is known to be a very long novel, okay? And I don't know, has anybody here read War and Peace? Okay, I asked this, and every year I asked, usually no one raises their hand. I did have one student raise her hand. She was Russian. And so I said, okay, well, that kind of makes sense. But I guess part of Crime and Punishment, I guess that's close enough. But yeah, so you have, yeah, so Leo Tolstoy, you know, Russian author, wrote some very long novels that kind of, you know, end up delving into kind of ideas of philosophy and stuff. Okay, so the end of War and Peace, you know, it ends with from the time the law of Copernicus was discovered and proved, the mere recognition of the fact that it was not the sun but the earth that moves sufficed to destroy the whole cosmography of the ancients. By disproving that law, it might have been possible to retain the old conception of the movements of the bodies. But okay, but anyway, this actually sounds kind of interesting, but also, anyway, what we're going to do is we're going to go through every single line in this big chunk of text, okay? So the code will read basically each line, you know, in a big chunk of text. And we could debate whether or not the English translation of War and Peace is a good model of the English language. Okay, so a big chunk of text, in our case, War and Peace. Okay, we'll read each line in a big chunk of text and count or tally basically each 2-letter combination. Okay, and so, you know, if this were our text, okay, this will be, you know, sample text from War and Peace. Okay, basically it will say space S plus 1, SA plus 1. It's going through each kind of two-letter things. Okay, AM plus 1, MP plus 1, PL plus 1, okay, LE plus 1, E space plus 1, space T plus 1, TE plus 1, et cetera, et cetera, et cetera. Okay, so it's going to go through and it's going to look at basically each two-letter combination in here, and it's going to tally them up. Okay, and the result, and so I ran some code, and I'm still kind of cleaning up my code here, so I'm not gonna share it with you just yet. So at the end, I get this big transition matrix, this 27 by 27 transition matrix that looks like this. Okay. And what we can see is that letter combinations like TH show up with high probability here. Okay. And then HE also shows up with high probability. And E space, okay, shows up probably with the high, among the highest probability, because I guess we have a lot of words that end in the letter E. Space T, we have a lot of words that start with T, okay? And then you look at certain rows like the row for J, and it is very, very light, okay? There's very few words that have the letter J in it, okay? There's maybe just a tiny bit of coloring here for JU, okay? I guess like judge and jump, but not very many else, okay? And you can kind of see rows and columns that appear a little bit darker, and they generally correspond to vowels like A and E and I. Okay, also N and O and things like that. Okay, and so you see certain combinations like ND is pretty dark, NG is pretty dark, ON, OR, OU, and things like that. You look at the letter Y, okay? Y goes into YO fairly frequently, and then there's a lot of words that end in Y and things like that, okay? Not a whole lot of X words, not a whole lot of Z words, and things like that, okay? So we've got, so this is going to be kind of the resulting matrix that shows kind of our two-letter combinations here, which let me put that in here. Okay. Oh, so fun fact, this letter transition matrix of basically which letter combinations are frequent. Okay, so this shows which letter combos are common. Okay, this actually powers your on-screen keyboard. Okay, so I don't know how old you guys were when the iPhone came out. Okay, so the iPhone was released in around 2007. Okay, and prior to the iPhone, so the iPhone was, I think, one of the very first phones that had only an on-screen keyboard. There was no physical keyboard, because prior to the iPhone, what was popular was the BlackBerry, and the BlackBerry had a physical keyboard with buttons, and you could actually feel every time you pushed a button, okay? And the reason why was that they had tried on-screen keyboards before, but people got frustrated with them because they would always have kind of typing mistakes, okay? And a big revolution came when Apple realized, you know what? When you look at the keyboard, you see the letters, and the size of each key is the same. But what we can do is we can actually change the size of the keys. We're not going to change what it looks like on the screen, but we're going to change the area of the screen that gets mapped to certain letters. So the size of each key, invisible to the user, the size of each key actually changed with each keystroke. And so you can actually try this out. If you try to, if you try to type the word thing, T-H-I-N-G, and when you try to type, when you do TH, if you tap the space in between G and H, okay, if you tap the space between G and H, it will register as an H. But then when you type in T-H-I-N-G, and for the G, if you tap the same spot between the H and the G, it will register as a G, okay? Because what's happening is your keyboard, after you type in the letter T, your keyboard knows that H is a much more likely letter than the letter G. So even though you're tapping the space in between G and H, that area gets mapped to an H. And then later on, after you type in I-N, T-H-I-N, it recognizes after N, the letter G is more likely than the letter H, okay? So after the letter N, G is a more likely letter to come than the letter H. And so that same area that got mapped to the H is going to get mapped to the G, okay? And it doesn't change anything on the screen. What you see on the screen remains the same, because if the keys changed every time you touch the letter, it would freak out the user. But if you try it, T-H-I-N-G, and you tap the space in between the G and the H, it's going to it changes what letter it gets mapped to, okay? And students always think this is a really cool thing, because it is really cool, and this really allowed on-screen keyboards to be adapted, because it allowed people no longer got frustrated with trying to type out messages on the on-screen keyboard, because people are actually really bad at tapping the letters on the on-screen keyboard. But people don't like to know that you suck at touching the letters on the screen, and they would blame the device. And so underneath it, they changed it to basically how they said, you know what, TH is a much more common combination than TG, and NG is much more common than NH and things like that. And so it changed basically the space where the letters get mapped. And so anyway, that allowed on-screen keyboards to be adapted, and basically that kind of technology has been applied to pretty much every single keyboard that you see on screen, and to the point where nobody has a phone with a physical keyboard anymore. But if you went back to 2007, people were scared of of using an on-screen keyboard, because it was they always had so many typos. But then but anyway, this improvement got implemented. Okay, so we're going to use this to help us evaluate the text of our words. Okay, of our potential kind of cipher mappings. Okay, and then all right. Oh yes, quiz letters. I guess I'll give you the last two right now, and then we'll I still have a little bit more to say, but last two will be the letters B and A. B as in bear, A as in apple. B as in bear, A as in apple. Okay, so what we're going to do next, okay, well, so looking at the two-letter combos is not going to get us all the way to the finished line, okay, finish line. So when we evaluate the probability of the text given a mapping, we're going to, this is going to be equal to basically the probability of our two-letter combos. And then what we will also have is we're going to have, to get us to the finish line, we need the probability of basically real English words. Okay, and so if we see real English words in our translated text, okay, so real words in the deciphered text, that will increase the probability of this potential mapping. Okay, and so so let me show you. So this will be achieved using kind of the assistance of something called a lexical database. Okay, so I have a lexical database which will list off. Okay, and this is basically a listing of words. And their relative English frequency, relative frequency in English. Okay, so the word the, if I look this up, okay, I get something around 5.27%, 0.052. So that's kind of the most probable word. And then, we'll look at other words. Okay, so, other common words, like the word in. Okay, that shows up around 2% of the time, 0.0196. Okay, but then, and other words are going to be less common. So we can do friend. Friend is on the order of 7 times 10 to the negative 5. And then if I do like friendship, that gets used even less frequently, 1.7 times 10 to the negative 5. Okay. And so anyway, the lexical database has a whole bunch of words and their corresponding probabilities. And then if you try to look up a nonsense word, right? So if I, instead of friendship, I type in some like a not real word, we get null, okay? Or basically something close, something like 0, okay? Basically, if the word doesn't exist, it returns null. And so, so anyway, we're going to use that to also assist us in figuring out the probabilities. Okay, so we're going to look at the 2-letter combos, and we want to find mappings that give us high probability 2-letter combos. And we also want mappings that will give us real English words. And we're going to kind of balance this. We're going to have some kind of term lambda to kind of balance and say, this is more important or this is less important or something like that. Okay. We'll take a look at this some more on Friday. I'm just kind of introducing you to some ideas here. On Friday, we'll take a look at some code. I've got to kind of clean it up a little bit, and we will apply that to try to decipher some kind of text message here. Okay. On Wednesday, you guys have your midterm exam, so we will see you guys on Wednesday, either at 10 a.m. or 10 p.m. Just show up again. And again, if you're going to take the exam in the evening, don't don't click around in the exam section Wednesday morning, and then just kind of the opposite. If you take it in the morning, please don't click around in the exam section in the evening either. Okay, so yeah, don't open up the exams. But we'll see you guys on Wednesday, either 10 a.m. or 10 p.m. And good luck as you guys study, and we'll see you guys then. So all right, have a good day.